Hello again. In this video, we're going to go over section 2.4, part 3, which is about locating vertical asymptotes. Now, in an earlier video from section 2.4, we talked about the definition of vertical asymptotes. But the definition of vertical asymptotes is not very user-friendly when it comes to finding the location of vertical asymptotes. So in this video, I'm going to show you how to find the location of vertical asymptotes when you have a rational function. Okay, so we're going to look at example 5, which happens to be a rational function, and we're going to locate the vertical asymptotes for this function. Okay, so let me show you how we do this. Okay, so there's really just two steps you have to go through to find the vertical asymptotes for rational functions. The first step is you have to reduce the rational function to lowest terms, and then you set the denominator equal to 0 and then solve for x, and that'll give you the vertical asymptotes. Okay, so let's try that with this function. So let's reduce this to lowest terms first by factoring this and seeing if anything cancels. So like this top polynomial will factor into x minus 1 times x minus 3. And then the bottom one will factor into x minus 1, x plus 1. And after you factor it, you can see that these will cancel out. The x minus 1s will cancel out. And that'll leave you with x minus 3 over x plus 1. Now, one thing I want you to be careful about is when you set this equal to x minus 1 over x plus 1, a lot of times we just write that those are equal, but technically this statement is not quite correct. It's not quite accurate. If these are equal, and I'm going to take this back off. So if this is really equal to this, what that means is for any x value that I pick, I'll get the same number on the left side as I would on the right side. But there's one number that we have to be very careful about. When I plug a 1 into the left side, I think you can see I get 0 divided by 0, which is undefined because division by 0 is not defined. Whereas when I plug a 1 in on the right-hand side, I get negative 2 over 2, which is negative 1. So I think you can see when x is equal to 1, you don't get the same number on both sides of this equation. You get undefined on the left, and you get, negative 2 over 2, negative 1 on the right side. So to say that these are equal without saying anything else is technically incorrect. And so how do we fix that? Well, here's how we fix it. Here's the issue. The issue is 1 is not in the domain of this function. I mean, if I plug a 1 in, I'm not getting a number out, which means it's not in the domain of this function. And so that should be the same with this function, right? 1 should not be in the domain of this function either. They have the same domain if they're going to be equal. And so we need to include this fact here. Explicitly, we need to state that x cannot be 1 here. Now, we don't have to state it explicitly here because that is implicitly known when you plug a 1 in. It's clear that you get 0 over 0, which is an undefined value. So 1 can't be in the domain of this function. But that's not implicitly known over here. Okay, when you plug a 1 in over here without making any statements about it, you get negative 2 over 2, which is negative 1. Okay, so if you can't plug 1 into this one, into this function, then you can't plug 1 into this one. You have to have the same domain. But over here, we need to state that explicitly. X cannot be 1. And if you say that, if you include that, then these two are actually equal for all x values except when x is 1. When x is 1, you get undefined in both cases. Okay? Well, I mean, you implicitly get undefined over here. Okay, we know that because you'll get 0 over 0. And then over here, we're explicitly telling the reader that you can't plug 1 into this function. Okay, it's not part of the domain of this function. And then if you state that, then these are equal. These two functions are equal for all those x values except 1. Okay, so having said that, this is now reduced in lowest form. So the next thing to do is set the denominator equal to 0 and then solve for x. And of course, set that equal to 0, and then when you solve for x, you just get -1. And this is actually a vertical line at x equals -1. And that's where your vertical asymptote is located. Now, one thing I want to point out is, let's say you wanted to find out where f of x was undefined. Okay, that's a different question than locating the vertical asymptotes. Well, where's this function undefined? Well, it's undefined anytime you get division by 0, and that happens when x is 1, but it also happens when x is -1. Okay, because if you plug -1 into this, you'll get 0 here. So there's two places where x is undefined, right? I mean, where f of x is undefined. It's undefined when x is 1, and it's also undefined when x is -1. Now, the reason it's undefined at -1 is because there's a vertical asymptote. But the reason it's undefined at 1 is not because it's a vertical asymptote, because there's only one vertical asymptote that we found. The reason it's undefined at x equals 1 is because there's a hole in the graph. And so I think the thing that we can learn from this is that when this x minus 1 cancels out, I mean, it's undefined at 1 and -1, but when it cancels out, reducing this to lowest terms, that is the location of the hole. So if it cancels out, that's where the hole is. If it remains, that's where the vertical asymptote will come from. Okay, so I think you can see that, right? X minus 1 cancels out, and so because it canceled out, it's not going to appear here as a vertical asymptote. And so that's the reason that was a hole. Okay, but the x plus 1 did not cancel out, so of course it remains here in reduced form. And when you set this bottom equal to 0, that's where the vertical asymptote came from. Okay, so I just wanted to point that out. Okay, so just be aware of this when you have rational functions. You set the bottom to 0 to find out when it's undefined. But it can be undefined for two different reasons. It can be undefined because it has a hole, or it can be undefined at that spot because it has a vertical asymptote. And so it's important to make this distinction. And that's why you have to reduce it to lowest terms first. Because anything that cancels out is the location of a hole, and anything that remains is the location of a vertical asymptote. Okay, so having said that, the last thing I want to talk about let's go back to the definition of vertical asymptotes for a moment. I mentioned earlier in this video that the definition of vertical asymptotes is not very user-friendly with respect to finding vertical asymptotes. I would never use the definition of a vertical asymptote to find the location of a vertical asymptote, at least for rational functions. I would just do it the way we just did it. That's a much easier way of finding vertical asymptotes. Having said that, let's go back to the definition of a vertical asymptote and just verify that the vertical asymptote that we found actually is a vertical asymptote under the definition of a vertical asymptote. Okay, so we found the vertical asymptote to be at x equals -1. Okay, so remember that. Now, remember the definition of a vertical asymptote, let's go back to that, says that the limit, if the limit of f of x as x approaches a as a two-sided limit is equal to plus or minus infinity, then you have a vertical asymptote at x equals a. If the limit of f of x as x approaches a from the positive side is plus or minus infinity, then you have a vertical asymptote at x equals a. Or if the limit of f of x as x approaches a from the negative side of a equals plus or minus infinity, then you have a vertical asymptote at x equals a. Okay, so any one of these three conditions would guarantee us to have a vertical asymptote at x equals a. We just need one of these three to be true. And it's basically you have limits at infinity as x approaches a as a two-sided limit, as a one-sided limit from the right side, or as a one-sided limit from the left side. Okay, so one of those has to be true to have a vertical asymptote at x equals a. So let's go back down to this example we're working on. And I need to remind myself again, we found the vertical asymptote to be at -1, okay? So we're going to approach -1 from the negative side. If we can show this is equal to plus or minus infinity, then that, by definition, says that x equals -1 is a vertical asymptote. So let's see. Probably the best way to evaluate this limit or find this limit is to graph this. So the graph of that function, the graph of this function looks like this. Now notice there's a hole at x equals 1, and there's a vertical asymptote at x equals -1. But let's verify it using the definition of a vertical asymptote. So as we approach -1 from the negative side, which means we're approaching from this side, you can see that the y value is heading towards infinity. Okay, and so that verifies by definition that x equals -1 is a vertical asymptote. By the way, you can also verify it by looking at the limit of this function as x approaches -1 from the positive side, because you can see as it approaches from -1 from the positive side, the y value is heading towards negative infinity. So that also verifies that x equals -1 is a vertical asymptote. Okay. Now, x equals +1 did not turn out to be a vertical asymptote, right? It turned out to be the location of a hole. And so if you were trying to show that this was a vertical asymptote, you would find that this limit apparently is not equal to plus or minus infinity. Otherwise, it would be a vertical asymptote by definition. And so if you look at this graph right here, as x approaches 1 from both sides of 1, the y value that it's approaching is actually, it looks like to be somewhere right here like at -1, but it certainly isn't plus or minus infinity. Okay, so that's pretty clear that that's not by definition, that is not the location of a vertical asymptote. Okay, I hope you found this video helpful. Thank you for watching. Bye-bye.